All right, so let me just start. So let me thank the organizers for putting together this extremely beautiful workshop, which I very much enjoy. And so I will add another point of view on relating gravity and condensed matter. And but after this beautiful talk on analog gravity, let me go back more to the ADS-CFT context and talk about new Kagome materials for holographic hydrodynamics. Okay, so let me give a brief motivation. So there are quite a few generalizations of the ADS-CFT correspondence, which are motivated by applications to hydrodynamics. And in particular, I think still the most famous result of this generalized ADS-CFT in view of applications is this very famous ratio for the shear viscosity over the entropy density, which was found by Goftonson and Styronets now back already. This was in 2004, actually. And this is this very universal result for theories at very strong coupling. And so these authors, of course, had in mind applications to the quark-gluon plasma, when you have a relativistic setup and in QCD. Nevertheless, this inspired a huge amount of applications in the context of applications of ADS-CFT. And there are actually further applications also for electrons in solids, which is a distinct subject, I would say, from using hydrodynamics in the quark-gluon plasma. Of course, there are some similarities and differences that will also show up in the talk. So the idea is now to investigate applications of ADS-CFT also in this context of electrons in solids. I should say that we are part of two big collaborations in condensed matter physics. So one is this excellence cluster CTQMAT, which is in the excellence strategy of the German federal government, which is a linked project between Würzburg and Dresden. So the talk by Johannes Koth yesterday. Johannes is also in this collaboration. And then we also have a so-called collaborative research center in topological and correlated electrons. And it's very nice that us, the ADS-CFT people, can take part in this now. And in fact, what I'm going to show you in my talk is a rather nice collaboration between our ADS-CFT group and some colleagues from our condensed matter department here in Würzburg. And this is actually this paper called Turbulent Hydrodynamics in Strongly Correlated Kagome Metals. And apart from our group, which involves Leni Meyer, who's I think also in the audience, and our student Jans Mathiakakis, who's also, I think also in the audience, we teamed up with our postdoc David Rodriguez, and then there's the group of Ronny Tomale, who is in the condensed matter department here, together with Domenico and Martin. And then we also joined forces with two condensed matter physicists from Bremen University, Erik van Loon and Tim Wheeling. And so this led to this paper in Nature Communications, which I'm about to describe to you. So the ideas of this paper is to propose a new Dirac material with stronger electronic coupling than graphene. And the name of this proposed material, which of course doesn't exist yet, is the so-called scandium Herbert-Smithite. So let me explain what this actually is. And so why are we looking at this? Well, this is in view of finding enhanced hydrodynamic behavior of the electrons and reaching much smaller values of the ratio of the shear viscosity over the entropy, as small as in this result, which holds at infinite coupling, and which gives you this very, very small number. So 1/4 pi is about 0.008, sorry. Okay, before I go there, and let me briefly mention that we have also some other work in hydrodynamics for electrons, more in the relation of actually looking at wires or channel geometries and see how the electrons move along these wires. So this is again with our group in Würzburg, and also we have a paper which I might briefly mention at the end together with our colleague Evelina Hankiewicz and her group. So I think Evelina was also taking part earlier. And this is some applications of hydro in these channel geometries, and also breaking parity invariance. Okay, but first, let me turn to some general statements to hydrodynamics for electrons in solids. So unlike in the quark-gluon plasma, the parameter window in which you can actually have hydrodynamics for electrons is much smaller. And so electron-electron interactions may actually lead to hydrodynamic electron flow if the photon and impurity interactions are suppressed. And so indeed, this is a rather small parameter window. So the electron interaction scale must be shorter than scales for interactions with phonons, impurities, or walls. So LEE is the typical scale for electron-electron scattering. And if this scale is smaller than the impurity scattering length, the phonon interacting length, and the wall of your geometry in which these electrons move, then there's actually a chance of seeing this hydrodynamical behavior. Okay, so in fact, there are some applications which were already studied experimentally in the context of this also this hydrodynamic behavior and also in relation to the shear viscosity. There's one rather early paper already from 1995, I think, by the group of my Würzburg colleague, Professor Molenkamp. And so there's actually a decrease of the differential resistance dV by di if the current is increasing. So this decrease is a very typical sign of this hydrodynamical behavior. Another set of experimental manifestations, a little more recent in relation to graphene. So there's quite a lot of papers there. Let me just cite this one as an example. It's a negative local resistance, which comes from a kind of backflow of this electron flow in this graphene context. And so far, most of the recent experiments looking for this are performed in graphene. Okay, but let me say something very brief about this decrease of the differential resistance. And in fact, in this paper, so the plot is taken from this paper here. This is the theoretical prediction and the experimental curves, where here's the current and here's the differential resistance. There you can actually nicely see this turnaround behavior. So there's a maximum, which is referred to as the Gauge effect. So here you this black, what you see in black here is the width of the wire. And if the electron scattering length is larger than the width of the wire, then you have a Knudsen flow ballistic regime, where the dominant effect is that the electrons scatter off the wall. And in that case, actually the differential resistance grows with the applied current. And then there's a turnaround to this hydrodynamic Poisson flow regime, where actually the electron scattering length is less than the width of the channel. And then, in fact, we see this hydrodynamic behavior, which in this Poisson regime means that the differential resistance decreases when increasing the current. And this is actually seen in these experimental measurements. So I should say that these experiments were performed in weakly coupled system, mostly gallium arsenide. And so this is a different setup than the graphene we were also considering on the previous slide. Okay, so now what determines the possible hydrodynamic behavior is this electron-electron scattering length. And at least in the perturbative regime, it can be shown that this scales with the inverse effective electron-electron coupling, which is given here. So this is the electric charge squared, the dielectric constant, and the Fermi velocity, which enter here. And obviously, since we are looking for very small values of this LEE electron-electron scattering length to increase the hydrodynamic behavior, so we are looking for larger electronic coupling, larger effective electronic coupling, in order to get more robust hydrodynamic behavior in this electron-electron scattering scenarios. And so far for most experiments, the material of choice here was graphene. And so there's actually a considerable theoretical and experimental effort to see hydrodynamic behavior of the electrons in graphene. On one hand side, there's this important property here that graphene is a Dirac material where we have this relativistic linear dispersion relation near the Dirac point, which allows to use a relativistic formulation of hydrodynamics. And let me just point out this review for this considerable theoretical and experimental effort that has been undertaken in this direction. A slight issue here is, however, that the effective electron coupling is not so large as to really completely obviously determining that we are in the hydrodynamic regime here. There are still some issues, so it would be nice to have a material in which the electron interaction is much stronger and LEE would even be much smaller in order to see unambiguously these hydrodynamic effects. Okay, let me discuss just a little further the effective size of this, the size of the effective Coulomb coupling in a more kind of kinetic theory recoupling approach as applied to graphene. So in fact, as was already discussed some years back, the effective Coulomb coupling grows logarithmically as a function of the temperature and is of order 1 for graphene in the hydrodynamic regime. Let me also point out this very thorough work in kinetic theory that was undertaken by Suresh Sachdev, who is also in this workshop, together with Jörg Schmangen and Fritz and Miller already also some years back, and they investigated this in a quantum critical scenario. And indeed, there is a quantum critical region in the plane spanned by the chemical potential and the temperature, where this eta over s, so the shear viscosity over entry point density, scales with the logarithm squared of the temperature. And outside this critical region, in fact, it goes like temperature to the -3rd power. Okay, so let's move towards the relativistic hydrodynamics. And let me just quickly recall this to you. I think there were quite a lot of discussions about this already in the workshop, so I can be brief. And so now, instead of looking at the hydro expansion of the current, we look indeed at the hydro expansion of the energy momentum tensor, which is the relevant quantity to find the shear viscosity as a transport coefficient. So this is the ideal hydrodynamic, and the shear viscosity actually shows up in a linear order in the expansion in derivatives of the 4 velocity. So you use the 4 velocity, this is some projector here. And so the shear viscosity appears here in front of this transversal term. There's also a bulk viscosity, but which is, however, absent in conformal systems, as are usually considered in the context of ADS-CFT. So we will focus on this coefficient here, which appears at linear order in the hydro expansion of the energy momentum tensor. Okay, so let me just very briefly recall how this shear viscosity is calculated in holography. In fact, it can be obtained from the propagation of a graviton. So the graviton is dual to the energy momentum tensor. And by just using standard methods of calculating correlation functions in ADS-CFT correspondence, we can obtain this 2-point function of the energy momentum tensor from the propagation of a graviton into a gravity theory and to leading order. And so for the largest coupling, the essential contribution in the gravity action is the Einstein-Hilbert term, which involves here just the Ricci scalar and the negative cosmological constant of the ADS-CFT correspondence. And then by performing this calculation, which I will review extremely briefly on the next slide, for an SUN gauge theory dual to this particular gravity theory at infinite coupling and also taking the rank of the gauge group to infinity, one indeed then finds this very famous result that I introduced in the first slide. So now what we did in this paper in view of making contact with strongly correlated Kagome materials is to consider the leading correction in the inverse coupling to this result. So to perform a strong coupling expansion in 1 over the coupling. And so the idea is to do this. So the materials we are going to consider are in 2+1 dimensions, which means that the gravity dual will be in 3+1 dimensions, which is rather important here in this context. And in fact, this leading correction will be obtained from terms in the curvature to the 4th power contributing to this gravity action. Okay, so very briefly, just let me remind you of this result by Kofton and Starinets of how they actually calculated this famous result. Right, so the energy momentum tensor is dual to the graviton. So the shear viscosity is determined by this Kubo formula, which involves the retarded Green's function of the transversal component of the energy momentum tensor 2-point function. And this can be calculated in ADS-CFT from propagation through the black hole space. And the result that is obtained is given here. On the other hand, we can calculate the entropy density from just the horizon area of a black hole embedded in this anti-de Sitter space. And just by taking the ratio of these two quantities, we get this universal result, which only depends on this natural constant and 1/4 pi. And obviously, there is this very notable relations to quantum critical systems in which the determinant time, the important time scale is given by h bar over k Boltzmann t, from which you can derive this dependent on h bar and k Boltzmann. However, this precise value of 1/4 pi is the key ingredient from the ADS-CFT correspondence here. Okay, let me just quickly say that a very nice ingredient in calculating these retarded Green's function in strongly coupled system using anti-de Sitter black holes is that there's no sign problem, and we get retarded and advanced Green's functions for free by imposing causality and suitable boundary conditions. So the quantum field theory is defined here at the boundary on this blue line, where our operators in the field theory are defined, and the dual fields can either come from the past or go to the future. And so the appropriate boundary conditions here then make sure that we have either a retarded or an advanced Green's function. Okay, now before calculating these higher order corrections, let me come to the Kagome materials to which we want to apply all of this to. So now this is more some explanations to my colleagues from ADS-CFT, because I think for the condensed matter physicists, this is extremely well known. So Kagome is a Japanese word, and it denotes a particular basket weaving pattern, which you can see in this picture. And so this is a very important topic in condensed matter physics. And so these Kagome materials actually reproduce this hexagonal lattice that is present in this weaving structure. And here you can see a picture of a structure of such a Kagome material. Now, the particular Kagome material that we considered in our paper was the so-called Herbert-Smithite. So this is named after an American mineralogist called Herbert Smith. And here you see the chemical composition of this material. So it has zinc, it has copper, oxygen, hydrogen, and chlorine. And so as long as we have a zinc sitting here in front, this is actually a material that exists and you can find in nature. However, our proposal will be to change the chemical composition of this material by replacing this zinc ion here by a scandium ion. So, okay, so this is our proposal, which you can find in this paper. So this original material, Herbert-Smithite, has 2+ valued zinc. And what is the case then is that the Fermi surface is actually below the Dirac point. So if this is my very rough structure of this Dirac cone in the band structure, then indeed the Fermi sea is somewhere here in this original material. And so now our proposal is to replace these twice positive ions by 3 times positive ions, the scandium. And this would entail that the Fermi surface is lifted, and it will be placed exactly at the Dirac point in this material, such that we get a Dirac material where the Fermi sea is precisely at the Dirac point. So that's the suggestion from the condensed matter side. And so then here's just to show you this material once more. So in this original material, the gray dots are actually zinc, and so that's where we will have the scandium, and then we have copper and chlorine and oxygen and hydrogen here also. And, okay. All right. So now our colleagues in the condensed matter group and also the colleagues from Bremen, what they actually now calculated for this new proposed material is both the band structure and the dispersion relations of optical phonons. And so here you can see the band structure along this most symmetric axis in the Brillouin zone. And indeed, so then this material has this Dirac cone here. And but what is interesting is that in the scandium Herbert-Smithite, the opening angle of this cone will be much wider than in graphene. So in graphene, we have this rather narrow cone, and here this will be much wider. And because the Fermi velocity actually enters very decisively into our effective Coulomb interaction, this will actually increase the size of the Coulomb interaction. Then as far as stability of this material is concerned, this optical phonon calculation shows to us that if we are at small but still reasonable temperatures, then at below, say, about 80 Kelvin, this material should be stable as far as optical phonons are concerned. So I should say, so for the calculation of the effective Coulomb interaction, our colleagues used a so-called constrained RPA technique. Okay, and then this is a result from the paper. So here we compare the Fermi velocity and the dielectric constant, and then the effective Coulomb interaction. So electrodynamics in vacuum obviously has 1/137. And then in this graphene layer structure, the coupling is somewhere between 0.5 and 1. And in this new material, what we find is then that this coupling will be about 3 times larger than in graphene, around the order of 3. And that will have very important effects, as I'm going to show to you. So, so this Kagome lattice, let me just summarize a little bit the condensed matter aspects of this material. So the Kagome lattice is formed from these copper oxide plaquettes. And so the difference to graphene is that the low energy physics is captured by some d orbitals at each copper site, rather than in graphene where you have p orbitals. And so that is, on one hand side, it ensures stability, but also it provides this much stronger coupling. And so the stability is also affected by the fact, or it's enhanced by the fact that when the Fermi level is at the Dirac point, then the filling fraction is actually 4/3 rather than half filling. And so this orbital hybridization allows for a larger Coulomb interaction, which is actually confirmed by these constrained RPA calculations that our colleagues perform. And so we predict that here the effective Coulomb interaction, will be about factor 3 bigger than in graphene. So we also found that the optical phonons are expected to be activated only above about 80 Kelvin. And putting all this together, we see enhanced hydrodynamic behavior because the electron-electron scattering length will only be about 1/6 of the one in graphene. So we suggest this material, which of course still needs to be synthesized as a candidate to test universal predictions from holography. So now, what exactly are these predictions? Well, so as I said, at recoupling, kinetic theory tells us that the leading term contributing to corrections to eta over s, or I would say the leading term at recoupling is of the order 1/α². Well, again, this is our Coulomb interaction. Now in holography, as I said, the leading term at infinite coupling is just h bar over 4 pi k Boltzmann. So what's the correction going to be? And as I already mentioned, and will explain to you on the next couple of slides, we argue that the leading correction in this strong coupling expansion that you get from holography will be of order also of the form alpha to the 3/2 here in the denominator. However, there will be a model-dependent coefficient C now in here, which is not, well, okay, so we don't know what the holographic dual of scandium halide smithite is. Okay, so there's a certain uncertainty which comes from the coefficient of this correction term. And so because we have this uncertainty, we decided to vary this coefficient through a huge range, okay, see lots of orders of magnitude, to see how our results are affected if we change this model-dependent coefficient. Okay, and so let me just briefly mention a few aspects of this ADS gravity computation. So as I mentioned, this material is in 2+1 dimensions, so the gravity dual is in 4 dimensions. And for this 4-dimensional gravity actions, we looked at corrections of higher order in the curvature, which in principle can be of the form r squared, r cubed, r to the 4th, and so on. And now the fact that we are in 4 dimensions actually simplifies the calculation quite a lot. So if we were to do the same for vial semimetals and where the gravity dual then would be in 5 dimensions, it would suddenly become a lot more complicated. So one term that comes to our head is that the r squared term is topological for the bulk theory in 4 dimensions. Of course, this comes from the fact that we have this Euler density, which was discussed earlier this afternoon in the context of the conformal anomalies. But you can actually also show that the vial tensor squared term does not contribute here. Then we can use some well-established result by Mitsayev and Zeitlin already from 1987 that the R cube terms should actually be absent in type 2 supergravity parent theories. So this term will also be absent. And then, of course, the next one that contributes is of this form R to the 4th. And this will precisely have this coefficient which scales like 1 over the 2th coupling to the 3/2. And by absorbing the factor of n into this constant, we then get our effective Coulomb interaction here in this term. Okay, so as I said, this coefficient is model dependent, and we parameterize it by varying the coefficient C over several orders of magnitudes, 4 orders of magnitude. And so this is now essentially the result that we obtain. So let me talk you through this picture and what we can learn from it. So here on the x-axis, you see the effective Coulomb interaction. And here you see the shear viscosity over entropy ratio in units of 1 over 4 pi. And so the dashed line corresponds to this value that the leading order term in this holographic calculation gives you. This you can see here. Now, so this picture is supposed to show you what happens if you match the weak coupling behavior. So here, as I argued at the beginning, from this kinetic theory analysis, there's a follow here with alpha to the -2. So this is given by this black line here. And then this blue band here, which you see comes from our holographic analysis of the first order correction. And so which we argue to be of the form alpha to the -3/2. And now the band comes from the fact that we vary this coefficient C. So let me show this formula again to vary the C over 4 orders of magnitude. And actually we see that the effect of doing that is not very big. And certainly for these values of the effective coupling, there's not a very pronounced effect, as you can see. So actually the model dependence is still rather small. So this is something you can see from this plot. Of course, it becomes larger when we go to the perturbative regime where ADS-CFT is no longer supposed to apply. Okay, and then we see that if we choose the value of this effective Coulomb coupling as is found in graphene, where I said it was roughly of order 1, so a little below 1. So that would be lying in this regime here. And this new material, which we are suggesting this scandium halbert smithite, that will be located here at about 2.9. So the advantage of having this material would be that we get much further into this regime where holography is potentially applicable, and we can study corrections such as this alpha to the -3/2 correction. And so this error bar line shows us also that the uncertainty in this coefficient C is much smaller in this coupling constant regime as compared to the regime where we have graphene, where the error bar then is much larger. So, and then we see that this material would be much more suited for studying hydrodynamic behavior of electrons in these Dirac materials. Okay, and a final advantage of using this material is that we could even reach potentially the turbulent regime. So we can actually estimate the size of the Reinhardt number, which determines whether we have turbulence or not. So that in the terms of the quantities that are relevant for such a channel with electrons, it's given by these quantities here. And so there's a typical velocity which is enhanced with strong coupling. And of course, the Reinhardt number enters the Navier-Stokes equation in this place here. So the point is that for actually seeing turbulence, the Reinhardt number must be of the order of about 1,000. And so in graphene, it's definitely too small. But in this new material that we suggest, the scandium halbert smithite, it will actually be a factor 100 larger than in graphene. And so there's a much bigger chance of actually seeing turbulent behavior, which would then have also very interesting effect in seeing vortices, interesting magnetic behavior, and so on of these materials. Okay, so I won't go for much longer. So this is all I wanted to say here about this idea of relating Kagome or synthesizing new Kagome materials in view of testing predictions of ADS-CFT. But let me just very briefly say also something about this hydrodynamic behavior that you see in these channel geometries. And in fact, by analyzing the hydrodynamic equations and choosing values of eta over s in this ADS-CFT regime, we do actually see this Poiseuille behavior of the flow. So as I mentioned at the beginning, so there is this differential resistance that decreases when we increase the current. And obviously also when the eta over s is very small, such as in this very strong coupling limit, then actually the absolute value of this differential resistance is small, and it certainly increases when we increase this number. And yet, let me also say that with this combined analysis of relativistic hydrodynamics and ADS-CFT, we can very nicely analyze the velocity profile in a channel. So this y is now basically the width, the coordinate spanning the width of my wire. So so in this picture, because it's pointing upwards, it means the wire goes in this direction, and we will flow in this direction here. And then we see that strongly coupled fluids actually flow faster than weakly coupled fluids due to the increased coherence. And okay, so this is interesting because now people become increasingly more able to actually experimentally determine the velocity profile inside such a wire. So again, so this is the width of the wire, and this is the velocity profile, and I think this is taken from this paper, which also has experimental results. And at the very end, let me just mention this collaboration with Irina Hankiewicz and her group. And so where again we considered a flow in a wire and with a velocity profile here, and where in addition now we also switch on a magnetic field, and then we can actually see an interesting, so there's parity breaking, and we see an interesting competition between the standard Hall effect and the so-called Hall viscosity, which is a hydrodynamic effect which comes with an opposite sign. And so if we calculate the voltage drop across the width of the channel, so again, if you have a channel like this and your electrons flow here, and we have measured the voltage drop across the channel, then it actually turns out that there will be a critical value for the magnetic field where the standard Hall effect is actually exactly compensated by this Hall viscosity. And then so the net voltage drop should go to 0 again. So that's what can be seen from this picture. Okay, so that brings me to the end. And so let me just conclude. So I suggested, I presented our work where we suggest the scandium substituted Herbert-Smithite with us having a predicted effective electron-electron coupling, which is 3 times larger than, 3.2 times larger than in graphene. So, and this may reach the region of robust hydrodynamic behavior of the electrons in solids and even turbulence. It leads to a much smaller ratio of eta over S than in weakly coupled systems. And then I also at the end briefly mentioned that we obtain Poisson flow behavior. If we now look at hydrodynamics in a kind of wire or channel geometry, we actually see that strongly coupled fluids do flow faster. And finally, I also showed you that we see a cancellation of the Hall viscosity induced voltage with the standard Hall voltage. So that brings me to the end of my talk, and I thank you very much for your attention. Thanks a lot.
Thank you for the great talk. Yeah, we have time for questions. Yeah, please unmute yourself if you have a question.
Sorry, no, I think can I ask a question, or was somebody's hand up before?
Sure, go ahead, please.
Right. First of all, thank you for your interesting talk.
Yeah, thanks.
I think this whole thing, I mean, it's very fascinating. There's one thing, because I have, I'm not from the community, it's not my field, so I have perhaps some very trivial questions, but what of these parameters, what can you really in an experiment measure or observe? Which ones? So what will be, could you break it down? So what will be the first thing to show that, that it's working, and then what more can you learn, and what are your observables, and how can you extract this information and put the feedback onto your theoretical calculations?
Yeah, okay, so here the point is that we calculate transport coefficients, okay? So this shear viscosity is a very famous example of a transport coefficient that you can obtain via a Kubo formula, okay? And so this particular transport coefficient appears in the hydrodynamic expansion of the energy momentum tensor. And then there's actually a very nice way in ADS-CFT how to calculate this shear viscosity, and then in this coefficient, the shear viscosity over entropy density, it's actually the fact that the ADS-CFT calculation gives you this universal value, and this has sparked a lot of interest. I mean, first more in the context of the quark-gluon plasma, and then later also in condensed matter. And the idea is precisely to see if this universal behavior, which is predicted by the ADS-CFT correspondence, shows up in some way in the lab. And so that's why we were looking at higher order correction terms, because of course it's not possible to reach infinite coupling in the lab, especially not in condensed matter. And so the next step that we are taking in this paper was to actually look at some corrections which within the supergravity approach. So I mean, my talk, similar to all the others that we're talking about chiral anomalies, is really using this expansion in terms of derivatives of the velocities. So the hydrodynamics are these long wavelength fluctuations. And then calculating these coefficients, these transport coefficients, these can also be conductivities, other examples when you have a charged fluid, and use the Kubo formula to calculate this from propagation of the dual fields via the gravity space, and then compare this with the experiment. Okay, I hope this kind of addresses it.
In the experiment, is there, I mean, you have experimental errors.
Mm-hmm.
Right? So you get this correction. Is there sort of an idea of are they above the experimental error? Can such a detection, maybe I'm asking too much, maybe it's just too early, but I'm just wondering where the field is in general, like how much, so beyond finding this universal behavior, and how feasible is it to do this experiment? And then what happens afterwards when you found it? Is this the end of it, or is there something more you're hoping to learn from it?
It's certainly not the end. Okay, so we are very much at the beginning. Okay, so I mean, this is nowhere near any precision. Okay, so the good thing about this new thing that we did is that we managed to do something about the correction at all. Okay, so so far people were working at the zeroth order, where there's this beautiful universal result. So now we are, this is super beautiful, but certainly in the condensed matter context, this is way off from any experiment. So now we are very proud that we managed to look at the first order correction, which brings us into a regime. We can scale down the coupling to come to a regime, which maybe by, for instance, devising this new material, we would be able to have an experimental investigation of precisely this type. I should say, I mean, there are many other very beautiful things, like this discussion of chiral anomalies yesterday and today. This is another example where people work in this direction. And one point is that it's very hard to determine the precise gravity dual of such a model. Okay, there's the gravity theories and there's the condensed matter model, and in principle, you know well how it works for this NX24 super young Mills theory, but that's of course very beautiful, but a little academical if you talk about condensed matter physics. Okay, so because there's this large n limit and so on. So then the question is more, how universal is this approach? So the idea is always to kind of extract universal information that is valid in many circumstances, rather than predicting for one particular material a very specific effect. I mean, so it's always the search for this universal behavior, which doesn't depend too much on the microscopic degrees of freedom. And if you have that, then this can be extremely useful, because you can calculate in a strongly coupled regime where there's really no other way of doing it so far. Especially these transport phenomena are very hard to calculate in any strongly coupled material. So yeah, I hope this somewhat addresses your, I mean, okay, I wouldn't say, you know, we want to understand quantum gravity by doing this. It's just also a very nice approach to understanding more strongly correlated materials, and by mapping it to some structures of black holes in this anti-de Sitter space.
Could I ask something?
Hi, Johanna.
Yeah, just a very quick question. You mentioned graphene at the beginning.
Yeah.
So this is maybe a silly question, but so in these twisted bilayer or multi-layer graphene,
yeah,
you kind of have, from what I understand, more strongly interacting systems. So have people thought about these questions for, say?
Yeah, actually, I had the same question.
The same question. Well, I think the statement is that in this new material that we're suggesting, if I'm not mistaken, this coupling of 0.91 is already for this. Wait, is that for bilayer? I'm not 100% sure, but I mean, certainly what I can say is that in this new material that we're suggesting here, the coupling will still be much larger than in any of these graphene models. I mean, so graphene, I mean, as far as I know, okay, I don't have the figure for this twisted bilayer graphene, but so in these films that people were considering, the coupling is about 1, and here in our case, it will be 3.2. So, and this, what we demonstrated here, that brings us much closer to the strongly coupled regime where these first order corrections to the gravity result become meaningful.
But your main argument was that in this material the Fermi velocity is smaller than in graphene, right?
Yes.
There was the argument, because in twisted bilayer graphene you can make Fermi velocity even to 0, so you can make it smaller as you want, as small as you want. So
okay, so okay, then I should definitely look at. Thanks for pointing this out. Okay, I need to check. But yeah, as you correctly say, this is just essentially the point. So where was this? If we look at our band structure, Yeah, exactly. So the main effect is, you know, this opening this wider. But so you say in twisted bilayer graphene, it should be.
Yeah, you can control it with the twist angle, and yeah, it's when you approach some special angle, it becomes smaller and smaller. So you can basically, you know, tune it to any point, any value you want. So,
excellent. Okay, so then let me just. So I will definitely look at that, and maybe the other thing then I should like to ask if I. Yeah. Okay. So the other quantity that enters here is this dielectric constant. Do you know anything about that in twisted bilayer graphene? And
well, I guess it should be the same as in graphene, roughly. I don't know, maybe just naive guess. But yeah, I don't really
okay,
know.
so you say this wouldn't spoil this effect. Okay, well then it's super interesting. I need to look at it. I wasn't aware that twisted bilayer graphene has this.
Yeah, I'll post some papers in Slack.
Okay, thanks. Yeah, no, that's excellent. Yeah, thank you very much. I wasn't aware of this.
Maybe can I comment on this a little bit?
Yeah,
So
sure.
there are measurements in twisted bilayer graphene of strange metal-like behavior with linearity resistivity at high temperatures. But just at a glance, it doesn't look like this material is in a relativistic regime. I mean, you know, for graphene, it's very clear that you can just focus on the vicinity of the Dirac node. That's not at all clear in twisted bilayer graphene. It seems like usually it looks more metallic. The chemical potential is not anywhere close to the Dirac node. So, I mean, maybe someday it could be a very strongly coupled Dirac material, but it doesn't look like that right now.
Yeah, thanks, Rubia, for commenting. So let me just quickly say that, I mean, let me just recall for this new material that we've been suggesting, this is just the point to, okay, so in this original Herbert-Smith height, the Fermi surface is actually way below the Dirac point. And this replacement of the zinc by scandium would just have the effect of bringing the.
Sure. No, I'm not. Of course, I agree with this. This is a very nice suggestion. I was referring to twisted bilayer graphene, where there are Dirac nodes, but they don't seem to be crucially controlling the transport as far as we can tell, at least the densities people have looked at.
And would you be able to do something similar to move in the twisted bilayer graphene, move the Fermi surface to the Dirac point?
Well, I suspect, as Grisha said, the velocity is so small that you have to be extremely low temperatures to be really seeing the physics of the Dirac node. You end up seeing, you know, that like the entire band.
I see. Okay. Yeah.
The moment, you know, in fact, you know, Grisha has a famous model where the band is totally flat, and then there's no physics of the Dirac cone at all in that limit. But yeah, but the real world is somewhere in between, and yeah, I think these are open questions right now.
But do you think if you go not to the magic angle, but just a little away from it, maybe you can still make it?
Yeah, that's a good suggestion. But the most dramatic strange, you know, graphene itself doesn't exhibit the strange metal behavior. It's a different type of relativistic strange metal, if you wish. It's not like cuprates sort of. So right now, the experimenters are more excited by true strange metal behavior rather than graphene-like behavior. I mean, to them, finding another realization of graphene is not very exciting because they already found it. But yes, I mean, I think what Igor was suggesting, maybe if there's some clear predictions on how relativistic graphene would be different from relativistic twisted bilayer graphene, that would be very interesting. And yeah, it could be in a much stronger regime, coupling regime. Yeah, okay.
Yeah, thanks a lot. So Grisha, I'm looking forward to seeing these papers then.
Okay, sure. Yeah.
Yeah, thanks Rubia for the comments. That was very useful.
Oh, no, that's a very nice talk. Thank you.
Yeah, thanks.
I see we have some questions in Slack. I don't know. I can all they look a bit too deep. So the first question is from Sirapat Lokrak. How does ADS-CFT describe the quantum phase transition?
Okay, so I think the idea is more, okay, so this is a question too severe, I would say, but the idea is more that up the quantum phase transition, we expect conformal behavior, and ADS-CFT, as the name says, is of course very well adapted to describing using a gravity dual, a strongly coupled conformal system, also at finite temperature, but especially of course at zero temperature. And so that's why many people, including Subir, suggested taking ADS-CFT to look at these quantum critical systems. Another, I think, very interesting fact is that this eta over S has this critical behavior because it scales like h bar over k Boltzmann. And the time scale that dominates quantum critical system is h bar over kt. And so you can derive this dependence of h bar over k Boltzmann directly from just analyzing a quantum critical system. So this added value of ADS-CFT is to find this coefficient of 1 over 4 pi. So these are two things I probably like to say, but of course there's much more. This is a very wide field, and of course many people have studied this in the last couple of years.
Okay, okay. Yes, there are no other questions. Okay, thanks a lot.
Maybe I should say, just coming back to this question, I think I should advertise Subir's book on this topic.
Thank you.
Yeah, I will post also Subir's book in our Slack. Is it okay, Subir?
Oh, of course. No, I mean, maybe another comment. I mean, the moment you say ADS-CFT, CFT means you're already at a quantum critical point. If you want to move away from the quantum critical point and describe a phase transition, you actually have to change the geometry from ADS to some other geometry. Yeah, okay.
Maybe I can add to this. Of course, there's many other models of gauge gravity duality where actually there's no ADS and no CFT, so that these have been deformed in some way to either break conformal symmetry, have renormalization group flows. So Igor is of course also an inventor of these things.
Okay, great.
So we can definitely have confining theories and add fields in the fundamental representation. I mean, there's many options of deforming ADS-CFT to more general examples of gauge gravity duality to study more complicated involved systems.
Okay, yes. I encourage everyone, please post your slides in your Slack channels so we can continue discussion there. And